So I hope you're having fun with the course so far. So in this tutorial, we will be discussing how to orient the molecules. We'll look at some complex molecules. I know we have already discussed the rules and all, how to orient the molecules in Cartesian coordinate system, but we'll take at least two examples which are little bit cumbersome to orient, and then we'll see what all precautions we have to take, because once you put a molecule correctly in Cartesian coordinate system, the rest of the job, like applying symmetry operations and all, becomes easier. So let us start with second tutorial. So let us discuss this. I have already given in home assignment, but let us discuss this case because the next molecule will be in comparison to this particular case. So let us discuss octahedral case. So to draw octahedral, I will draw it as a rectangle, something like this, where at the vertices I have 4b atoms, and these are my AB bonds. And then there is one B above the plane and one B below the plane, right? So now this is my XYZ. So this particular molecule is rather straightforward. I mean, it looks complex, but it's straightforward in the sense that the A goes in the center, and then you have B on the top and B at the bottom. Those are, let me draw the bonds with different colors. And the other B, one of the B's will be onto this axis, and the other B will be onto this axis. Right? And all the bonds, and this is the triangle which we have drawn here. So it's something like this. So my principal axis is C4 axis, which is oriented along Z axis. So C4 is along Z axis, and then the XZ plane has to have the highest number of atoms. So in this case, YZ and XZ plane would have equal number of atoms. So this is my XZ plane along which I have 3B atoms, right? So if I mark it as 1, 2, 3, 4, 5, 6, my XZ plane contains B1, B5, B6 and A, right? And similarly YZ plane contains, YZ will have B1, B5, B6, B3 and A. So XZ and YZ plane in this case contains equal number of atoms, but if there is any confusion, XZ plane should contain more number of atoms as compared to YZ plane if there is discrepancy here. Okay, so this is rather easier. And while we are at this molecule, let us also list down the symmetry elements and corresponding operations, right? So what are the symmetry elements present? The first and foremost is E, followed by C4, the C4 which is along Z axis. Now also C4 will also have, there would also be a C2 along this. Then there would be C2 prime, C2 double prime. So C4 is along Z axis. Now C2 is also along Z axis. C2 prime, this will be perpendicular to Z axis. So it will be either X or Y. So there will be two C2 primes, right? Then similarly, there will be how many C2 double primes? So C2 double primes, which is bisecting the XY axis. So there would be two C2 double primes, and there would be I, Then we have, we will do this counting. I'm just counting from the top. So we'll do this counting again. So we'll see, we'll have S4, then S6 will be there, and there will also be a C3. We will see where the C3 is, how many C3s are there. S6 is there, sigma H is there, and sigma D is there, right? Now let us try to count how many such axes are there. So one of the C4 is along Z-axis. Similarly, another C4 will also be along X-axis and Y-axis. So there will be 3 such C4 axis. Now about C3, where is the C3 axis? So if you try to draw this molecule in a way where you can, so this is my A, this is B, 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 and this is not all B's in plane. So all the 3 B's are coming actually out of the plane of the board, and these 3 B's are coming at the back, going at the back, so behind the plane of the board. So this is how my C3, now the C3 will be perpendicular to the plane of the board. So if you see, I'm looking through my XYZ axis. So each of this is XYZ and I'm looking through it, right? So if you see that my C3 is actually equiangle. So C3 is equiangle from X, Y, Z axis. Okay, it is somewhere in the middle of X, Y, and Z axis. So I'm looking at B2, B5, and B3. So this is my B2, B3, and B5. And at the back is B1, B4, and B6. So I hope you can easily see this. Okay. So how many such C3s will be there now? So you have to find such triplets. So you have one such triplet here, then you have B3, B5, B4, another triplet, and then you have B1, B5, B2. So you have to keep on counting all such, and then you will see that there are 4 such C3 axes. Okay. So if you want, we can list it down. So you have B2, B3, B5. So you are passing through this, and you're also passing through, you're also rotating B1, B4, B6. This is one C3. Now second C3 will be, if you, let's say if you count B3, B4, B5, B3, B4, B5. So if you count this B3, B4, B5, the rest of the 3 will be B1, B2, B6. B1, B2, B6. You will be rotating this. This is my second C3. Okay. Now third C3 can be, now B1, B2, B6 is done. So it can be B at this back. So B1, B4, B5, right? So B1, B4, B5. Okay, and so on. So you can count that there'll be 3 and then 4 C3 such axes. Now C2, which is along Z axis or which is collinear with C4. So if there are 3 such C4s, then there will be 3 such C2 axes. Okay, about C2 primes. So C2 prime will be along X axis and along Y axis if we are considering the flipping of B5 and B6. Okay. So you can say that one of the C2 prime is along B2. So C2 prime is B2, A, B4. Okay. The second is B1, A, B3. Then there would also be another one which is along. No, this is the C2 prime which we are talking about, right? So no, I think there is some mistake. This would be altogether 6 C2 primes. So C2 primes, let us list them down. So not these ones, because these ones are actually these C2s which are collinear with C4. So we are not talking about these ones. Let's see. So you have C2 primes which are now in between the bonds. So which are the 6 C2 primes? So you can see that it is B2A, B3 bisecting B2A, B3, this angle. Then at the same time, this will also be bisecting B1A, B4. Okay, and it will be flipping B5A, B6 or B5 to B6. Okay, so this is one. Now let's also find another such pair. So you have B1A, B2, B3A, B4. So these are the angles which this C2 prime is bisecting. Now this is one, this is one. Similarly, you have one going in XZ plane. So this was in XY plane. Both of these are in XY plane, right? So similarly, you will find two pairs in XZ plane and two pairs in YZ plane, right? So that gives you 6 such C2 primes. I is only 1. S4 will be equal to the number of C4 axes. So if you have 3 C4s, you will have 3 S4s. S6 should be equal to number of C3 axes. So if there are 4 C3 axes, so there will be 4 S6 axes. Sigma H, so you have XY plane as the sigma H, then YZ plane, and then the XZ plane. So that means there will be 3 such sigmas, and sigma D's will be now coplanar with C2 primes. So if there are 6 C2 primes, you have 6 sigma D's, right? So I hope I have not made it more confusing, but I would suggest you to work out this example again by yourself so that it is very, very clear. Now let us go to a even difficult molecule than this one. It's not, well, the molecule is not difficult. It's just that it is, visualization is sometimes more cumbersome. Okay. So now let's see that I have same molecule A. The central metal or the central atom has the similar octahedral symmetry. But now I have these two connected with bonds. Okay, so now the case is not as simple. So now if you try to draw this molecule again in the same fashion, it will not work. So if I'm trying to draw it like this, and then I'm saying that I have connected these, then it will not work. Okay, this is my X, Y, Z, minus Z, minus X, minus Y. All right. So let us say that this is it. So now what are the symmetry elements? Can you identify the symmetry elements here? So if you look at the octahedral case, we had E. So E will still be existing. C4, which was collinear with Z-axis or X-axis or Y-axis, ceases to exist, because if you try to do a C4 rotation, this particular B comes here. So let us number these 1, 2, 3, 4, 5 and 6. So B3 goes to B1 if I do a C4 axis, and B1 goes to B2, right? Now if you do that, let's try to do this operation C4. Let us see. So you have A. So now I have B1 here and my B3 comes here. Okay. And what happens to B2? B2 goes here. and now B3 and B2 are connected, right? B3 and B2 are connected, and what happens to B4? B4 comes here, right? B4 comes here, and my B5 and B6 remain as such because this is C4 along Z axis. So B4 was connected to B5 and B1 is connected to B6, right? Now you see that these bonds, if I do a C4 rotation, these bonds make these two configurations different. So I can say that one is not equivalent to 2, right? Whereas in case of octahedral, because these bonds are not there, so 1 and 2 are equivalent, so that's why C4 exists. In this particular case, C4 does not exist. So if I cannot have C4 axis, which is my principal axis in octahedral case, so in this case, what is my principal axis? So the next order axis was, in that case, it was C3, right? So let us see if the C3 axis exists. So let us try to draw this molecule in the way so that we can easily draw a C3 axis. So you have A, B. So this is B5. Then I have B1. Then I have B2. Okay, so I'm looking from center of the XYZ side. Okay, and at the back I have B3, B4 and B6. And now what all are joined? B1, B6 is joined, B4 and B5 are joined, B3 and B2 are joined. And now my C3 axis is perpendicular to this plane of the board, going through these triangles. Okay, going through these imaginary equilateral triangles. Okay, there are two such triangles making a star-like appearance. Now if I do a C3 axis, so we want to see whether C3 axis exists or not. So because we are trying to find out what is the principal axis here. So if I do a C3 operation, what do I get? We have to also carefully see if the bonds remain at the same positions. These will remain at the same positions, but if the bonds are also same. So this is my B1. So B1 goes here, B2 comes here. It's an anti-clockwise rotation with 120 degrees, and B5 comes over here. Similarly, B6 goes here, B3 comes here, and B4 comes here. Now original connections were B4 to B5, okay, then B1 to B6, okay, and B3 to B2, okay. So now if you see that the bonds are also at the same position, so I can say that my configuration 3rd and 4th are equivalent, right? So then I can say that C3 is existing. So that means my C3 is actually the principal axis. Now the rules of assigning the molecule to a coordinate system says that you have to align your principal axis to the coordinate system, right? So now how do I assign this molecule? So that would mean that this is not a correct representation of the molecule along the coordinate axis. So this is not the correct way. Okay, so what is the correct way then? The correct way would be if you draw this molecule so that my z-axis is along C3 axis. How do I draw my z-axis along C3 axis? So if I'm looking from the top, something like this, this is my x, y, minus x, minus y, and this is at the origin my central atom. Now xz plane should have more number of atoms as compared to yz plane or any other random area. So then I will draw one of the bonds which is coming out of the plane of the board as along xz. So this is my one bond, this is second B, this is third B, right? Similarly, the opposite end will have 1B, second B. So if you want to draw the same triangle or same rectangle which was drawn here, so these are the four atoms which are forming the rectangle, and these are the two opposite atoms. And where are the bonds which are connecting? So these are the bonds which are connecting the 10 B atoms, right? So if you orient the molecule like this, you should be able to find out what are the other symmetry operations. So for example, now C3 axis is along Z axis, which is clear. So that makes my principal axis. So what are the symmetry elements? I have E, then I have C3. Then what else I have here? How many C3 axes are there? That also we can see. How many C3 axes will be there? There will be one C3 axis. Okay, and then you have C2 axis, and that will be all. Where is the C2 axis now? So C2 axis will be, so if I, C2 axis will be in between X, Y. This will be my C2 axis. Similarly, there will be another C2 axis, which will be like this. Right? So that means I am reflecting this B with this B, this B with this B. Okay. And if I'm doing this one, then I'll be reflecting these two B's and these two B's, right? And then these two B's. So let us try to work it out. Let's draw this molecule and see how the C2 axis works actually, because otherwise it will remain as a confusion. So let me draw this molecule again. This is my X minus X, Y minus Y, and the molecule looks like this. You have A, B, so these are all 120-degree angles. Excuse me for the bad drawing. Then you have B, B, B. Now if I name them, so you have 1, 2, 3, 4, 5, 6. Let me now draw a C2 axis which is bisecting B4 and B3 and B1 and B2. Okay, so if I do this will actually be a, let us draw this molecule again maybe, because the angles are not appearing correct. So let me just draw it again. So let's be more careful in drawing. X minus X, Y minus Y. So you have okay, so I've tried to keep this angle as 30 degrees. Then I have, and these are wedge like projections. Okay, and then this one would also be like 30 degree. So this angle is 30 degree, this angle is also 30 degree, this is 60 degree, 60, 30. Okay. So now this is my, these are my B's. So it looks better than what it was earlier. So you have B1, 2, 3, 4, 5, 6. Okay. Now, where is my C2 axis? So C2 axis will be reflecting B2 and B5. So let's also first connect the bonds. So my B3, B5, B1, B2, B4, B6. Let's say these are the ones which are connected. So if I now do this reflection, then my B2, B5 will be replaced, B1, B3 will be replaced, and B4, B6 will be replaced. Okay. So then if I do this, I will still have it. So we have to see if the bonds are also reflected accordingly. Okay. So this is my B, 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 B. Now I said B2, B5 will be reflected. So B2 and so B5. Then upon doing C2, B4 and B6 will be reflected. So B6 goes to B4 and B1 is replaced with B3. Now the original connections were B1, B2, B3, B5 and B4, B6. So my bonds are also in the same place. So I can say the first is equivalent to configuration 2, right? So that's how C2 will be reflected. C2 will be existing. So the only elements in this particular case will be E, C3 and C2, and there will be one such C3 and 3 such C2 elements. We can of course find out what are the number of corresponding operations, but we can see that there are 3 such C2s. See, one is between minus x, y, minus y, x. Similarly, another will be from this side, and third will be from using the z-axis as the plane, right? So there'll be 3 such C2s present. Okay, so that reduces a lot of symmetry elements as compared to the octahedral molecule. Once we join these atoms with bonds, the octahedral group reduces to a very small number of symmetry elements. We'll see what are the point groups and all, but let's not go into those details. So I hope the visualization part, which is very, very important for this course, is now clear to some extent. We should be also practicing a lot of molecules. Pick up any molecule, look out any object around you, and try to find out what are the symmetry elements and symmetry operations. I'll give you some example. For example, try to find out for letter E, what are the symmetry elements present. Try to find out for the word mom, okay, what are the symmetry elements present. It's a 2D picture, let's say. Try to see, for example, a hexagonal sharpened pencil. Okay, try to see what are the symmetry elements and operations present. So pick up any object around you and see which has some symmetry. See what are the symmetry elements present, so that this particular concept of visualization is very, very clear in your heads. Okay, otherwise it will keep on getting accumulated, and you will face a lot of issues in the later part of the course. Okay, so that will be all. Any questions, please shoot me an email. Thank you.